Okay, everybody, so welcome to this lecture 3. So recall that the last day we discussed ideals. So let's just recall the definition of that again, because this is something we're going to be using throughout this lecture. So a subspace, a linear subspace inside an L, for L Lie algebra, is called an ideal if if the commutative bracket of L, the whole Lie algebra with I, is contained in I. Let's also remember this notation just means the set x I, where x is contained in L and I is contained in I. Just a compact way of writing this. That's what an ideal is. In analogy with the usual notion of an ideal in ring theory. Note as well that because of the anti-commutativity axiom of the algebra, this is equal to I L. They're the same thing. So there's no notion of a left and a right ideal in the algebras. It's like in commutative ring theory where left and right ideals are the same thing. So that makes your life easier. Now remember, we had an example. SL2 has no non-trivial ideals, i.e. not 0 or L. Sorry, this is the example SL2, so this should be SL2. Trivial ideals are going to be either 0, clearly trivial because whenever you commute, take the Lie bracket of anything with 0, you're going to get 0. And when you take the Lie bracket of the whole thing, then of course, because it's a Lie algebra, you're going to get something that lands inside an L again, because you're considering the whole thing. SL2 is no non-trivial ideals. So not every Lie algebras do not need to have non-trivial ideals, and in fact, there's a large class of them which don't. Very important class of them, which will form the basis, actually, or the majority of what we're building towards, or the main results that we're building towards in this course. So we call something like this simple. Okay, it has no ideals. So somehow these are simple Lie algebras are like building blocks, or they're like parts with no internal structure. They're like atoms in their own right somehow. And I think of them in nice analogy might be to prime numbers as well. Okay, so you can't break a prime number into different parts, and this you can't really decompose it. It's a simple object on its own. There's no decomposing it. However, there do exist Lie algebras which are definitely very far from simple, and which contain a large collection or a sequence of ideals inside them, and they exist somehow at the other end of the spectrum of Lie algebras. So one end you have simple, and at the other there's no ideals, and then over at the other side of the algebras you have things with lots of ideals. And that's kind of, I guess, Lie algebras is sort of somewhere. You can sort of look at Lie algebra, and one question you can ask about it is, does it end over here? Does it have lots of ideals, or is it simple over here with no ideals? It's just a block. And that's kind of a Lie algebras are somewhere. All Lie algebras are somewhere on this range. So today we're going to be talking about Lie algebras which have ideals, particular, a special type of Lie algebras which have ideals. Before we do that though, let's do a small technical lemma. I don't recall if we did this the last day, but if we did, it's good for you to see it again anyway. The proof is easy. So let's just take a lemma. And this is something where we're going to construct ideals from ideals. Okay, so just a small trick. So if I is an ideal of L, we start with the Lie ideal. What ideal are we going to construct from it? Well, then Li is an ideal. Okay. Now, look up here. We see that Li is contained in I. Okay? The Lie bracket of L and I is contained in I. But it does not mean that it's equal. It can be equal. I mean, for example, if you put L and simple Lie algebra, because L is an ideal, then you have to get back to the whole thing again. Unless it's trivial, then you would get 0. Sorry, unless it's abelian, then you would get 0. So there are your two options. But if it's a non-abelian Lie algebra, then, like here, for example, SL2 is equal to SL2. Because not every Lie bracket is 0, therefore it can't be 0, therefore it has to be the whole thing. You've got two choices. So this is not necessarily an equality. Sorry. Yes, that's correct. This can be a proper inclusion. It can be an equality or it can be a proper inclusion. But this is saying that no matter what it is, whether this is an identity or a proper inclusion, it's still an ideal inside an L. Okay. But we prove this, well, this is very easy actually. So let's look at X, Y, and I. Okay, so we'll have X and Y contained in L, and I contained in I. So that means that this thing here is contained in L, I. Now we want to show that this, because this is our UI. Let me write it in red. This is J. We want to show that this is contained in L and J. But we know that this guy is contained in I, because I is an ideal. So it's equal, if we denote this with small, that's denoted by I prime, okay? Then this thing here is equal to X I prime, which is clearly contained inside in L I. Sorry, this is obviously stupid. They wanted L J is contained in here. Okay? This is the definition. Sorry about the stupid mistake. So this actually says that it's true. The commutator bracket, this guy, actually lives inside here. So now we can just get rid of this. Let's get rid of this. And so this guy is contained in this, therefore it's an ideal. Okay, so very, very easy consequence of the definition. And this is a way of, just to repeat myself, when you have an ideal, you can always construct another ideal from it by just taking the commutative bracket with that ideal. Again, as I said, you're not guaranteed to get something new. You may get back the same thing, you may get 0. But if you do get a new ideal, then if you do get a new space, if the commutative bracket is a new vector space, then this vector space, it is guaranteed to be an ideal again, in the whole space. Okay. We're going to use this trick now to define nilpotent algebras. Okay, so I'll give you 1 second if you want to. Okay, and we'll erase. And now we're going to restrict to L being finite dimensional. Just because for convenience, everything will be a finite dimensional Lie algebra. And as well, really, we're interested in Lie algebras that are ultimately going to come from Lie groups, as we'll see later on in the course. And these are going to be finite dimensional manifolds, so the associated Lie algebras will always be finite dimensional. So our main focus in the course is really on finite dimensional Lie algebras. But I'll say whenever I'm assuming that we're working with something finite dimensional. So L, B, finite dimensional Lie algebra. Central series of ideals so what is this? It's just going to be a series of ideals. It's just going to be a collection of ideals labelled by the natural numbers. Okay. So for the natural numbers, and usually use Z, denoting whether they're greater than or equal to 0. This avoids any terrible discussions about whether 0 is contained in the natural numbers a lot. Okay, so the integers which are greater, strictly greater than 0. Okay, so we start with L. It's just our starting point because we need to start somewhere. And what do we do to go? Then we define them inductively. So we define n in terms of the previous ideal L minus 1. Okay. That's how it works. Now, we know from the previous, so what should we note? Well, will I define? Yes, before I'll make some comments on this definition, let's try to take it apart a little bit. But before we do that, let's introduce the definition of nilpotent. So L is called nilpotent if if at some point these commutators reduce down to 0, you keep on applying this inductive process, and if at some point you get to 0, then it's called nilpotent. So what can go wrong here? I mean, if it's finite dimensional, then if the dimension keeps increasing here, it has to go to 0. However, that's the trick. If the dimension decreases, and that's just like I was saying before, when you take Lie products of subspaces, then, or you take the Lie product of an ideal with the whole thing, you're not guaranteed, and quite often it will not happen, that you actually get something smaller. It can be that there's an inequality here. So that's what could stop it from being nilpotent. That could stop the dimension from getting lower and lower. And you see that if this sequence stops now, if it turns out that L of n is equal to L of n minus 1 at some point, then this will continue. And that's it, then nothing can happen. You'll never get something smaller. So it's somehow, that's what you should try to remember again, is that's starting to look something like a simple Lie algebra, because this trick for constructing a new ideal just gives you back the old ideal that you started with. That's something that would necessarily happen if you got down to something which is simple. So it's a way of constructing, I guess, either you go down to 0, or it's a way of getting a sequence that's going to go towards a symbol, roughly speaking. Anyway, so if it does go to 0, then that's what's called nilpotent. Let's now start some remarks. Now we can do the remarks. So, what have we got? We've got central series of ideals. We know that these are ideals because of the previous lemma. What else? Let's give, I guess this can be a lemma. So, I hope you're familiar with this. Let me just write it out if you're not. I will use this throughout the rest of the course. It's the following are equivalent. Okay, so just taking the definition of a nilpotent algebra, that the central series of Lie algebra ideals of L actually end up being 0 at some point. Second, x1 is 2. Here, for all xi, no, it's for all xi, yeah, and m. Okay, so I think this should sort of make sense, because this guy is just going to be all elements of this form. So if this is equal to 0, then all of these guys have to be equal to 0. That's what it means. It means that the only elements inside this subset are actually 0. The only element inside it is 0. Or equivalently, just expressing this as the adjoint, see that I can have, this is the adjoint action, this bracket of xn and xn plus 1. And so on and so on and so on. So in fact, you can really think about this as add to x1 after, well, let's do it over here. So if I have add okay, that's what this guy is. And then with the next bracket over xn minus 1, that's just going to be acting on this thing. by x minus 1, so that's just the adjoint x of n minus 1, and all the way back to x1. This should be equal to 0. Okay? Or equivalently, for all x up in L. But we can just get rid of this, because if we get rid of this, it means that this linear operator is equal to 0. What does it mean for a linear operator to be equal to 0? It means that it operates as 0 on every element. So that's the same. Okay, so there's 3 different ways to formulate this. And in particular, this implies, and this is to explain some motivation for the name nilpotent, because you know what a nilpotent operator is, I hope. It's just going to be an operator or an nilpotent element, more generally. If you operate on it often enough, you get to 0. And that would mean that add of x is nilpotent. Or it is a nilpotent operator. Or even a matrix as we're dealing with something which is finite. I mean, a nilpotent matrix as we're dealing with something which is finite dimensional. Okay? So just take, these don't need to be distinct. You can consider them not distinct. So then, putting x everywhere here, that will have to be 0. We'll have to operate on every element of the algebra 0, which means this is an nilpotent operator, which tells you somehow, gives you an idea where the name comes from. Alright, so there's some remarks. Quick summary again. What are we trying to say? In one extreme of the algebras, we have things which are simple. They have no ideals. They can't be decomposed further. They have no sub-objects inside them. Well, some of them have no ideals. And then the other, if you do, if your algebra is not simple, then one way to study it, to sort of break it apart, is to look at these sequences of ideals. They're not guaranteed to eventually arrive at 0. The dimension can get smaller or stay the same. It's not guaranteed that it will actually always get smaller, so it may not terminate and eventually end up at the 0-dimensional space. But if it does, we call it nilpotent, and they're a very special type. So let's prove a theorem about nilpotent algebras. First proper theorem we're going to prove due to Engel. Alright, so before we list the consequences, let's just see what we have in the setup. So let A be a Lie algebra, as usual. It's going to be finite dimension, actually. And let, yeah, I guess I should wait because, and let V rho be a non-zero finite dimensional representation of L. Okay, so we spoke about representations last week. We're thinking, we had the two formulations. We had one in terms of modules and we had one in terms of maps that go from the vector space into the endomorphisms of some vector space that you're looking at. Go from your Lie algebra into the morphisms, the endomorphisms, the linear endomorphisms of the vector space that you're looking at, such that they bring, it's a Lie algebra map, so it's going to bring the Lie algebra product to the commutator bracket. So it's, Lie algebras are somehow generalizations, Lie algebras are generalizations of commutator, the commutator bracket on the endomorphisms of the vector space, commutator bracket of matrices, and a representation is somehow bringing them to a concrete, it's a concrete formulation. It's somehow taking the abstract Lie algebra and bringing it to the very concrete example that we're generating. And we assume that it's a finite dimensional representation. Okay. The vector space V on which it's represented is finite dimensional. And note that for every x in L, every element of the Lie algebra, this guy is nilpotent. It's a nilpotent operator, so it's just, this whole rho of x is just an element of the endomorphisms of V. If you choose a specific basis of V, then of course this would just be the matrices. Is nilpotent, which is to say if you apply it often enough, then you get to zero. Okay, so we're seeing here a connection between nilpotent Lie algebras and nilpotent operators again. So what happens for the first one? Well, you see that there exists, again backwardly for exists, I guess this is common, well known to you all. There exists a non-zero V, non-element small v in big V, such that rho of x is rho of x acting on V. Okay, rho of x is an endomorphism of V. V is small v is an element of big V, so it can act upon it linearly. Is equal to 0 for all x in L. Sorry, I thought I made some stupid mistake there, though, I think it's okay. For all L, i.e., there exists an invariant element so this word here, that's just, remember we defined this last week, we said that an element inside in a representation was called invariant if it was killed by every element of the Lie algebra that we're representing. Just a name, and just repeating the definition. Okay. So, given such a setup, we have an invariant element in the representation. 2. There will exist a basis of V such that rho of x by such that there will exist a basis of V. Okay, we can make a choice of basis of V, such that for all x, an element of L, f rho of x is strictly triangular. With respect to this basis. Alright? So we make a choice basis. That gives us an isomorphism between the endomorphisms of V, the linear endomorphisms of V in the matrices, just like you know from basic linear algebra. And then what we're saying is that then we can ask, so looking at considering this now as a matrix with respect to the identification of the endomorphisms and the matrices, there will exist a basis such that these guys, every element of row of every element of the Lie algebra is a strictly upper triangular matrix. Okay. So this is the first indication that nilpotent algebras look a lot like upper triangular matrices. Three, there exists a filtration such that Right, so what I mean by filtration here is just that you have a sequence of vector spaces such that V0 is contained in V1, is contained in V2, and so on, all the way up to the top. It's just some sequence of vector spaces. And with respect to that sequence of vector spaces, V is going to bring L, sorry, I should say, is going to act on Vk and brings it down. So the L moves you inside it brings you from the total into this, well, instead of Vn-1, into the subspace, again into a subspace of this, into a subspace of this, and all the way down eventually until you get to 0. Okay. So it's somehow measuring the nilpotent degree of the thing. It kind of makes sense, again, hopefully. Remember here, I kind of made this look like an operator, which of course it's not. What this means is going to be, well, let me write it out. Hopefully you can see this. This is just going to be x by vk, well, it's x by v for all x an element of L and v an element of Lk. Just a short way of writing that. So when you take anything inside here, you operate on it by any element of L, then you're going to get into the one below. And so on and so on. Okay, so this is proof that Theorem by Engel is about representations of these algebras, which is going to be something that basically, we're not assuming that that's nilpotent, but we are assuming that the representation is somehow nilpotent, which is to say every element is a nilpotent operator. This is going to be a technical tool that we use in the next theorem. Which is basically going to give us a criteria for nilpotency. So this is a technical theorem that we're going to prove first of all. Okay. So hopefully you've taken in the statement of it. What we're really going to do is we're going to postpone the proof of 1. What we want to do first is we're going to prove that this implies 2 and this implies here, and we're going to put this into the future and prove it a little bit later. So the first step will be proving that 1 implies 2 and then 2 implies 3, and hence, of course, if 1 implies 2, 2 implies 3, then we know that 1 implies 3 as well. Alright, so let's erase this and make some space for the proof. Okay, so let's start with the proof. How are we noting it? Yeah, 1. So 1 implies 2. Alright, what we're going to do is we're going to use an inductive proof. So I won't fill in fill in the basic details. Let V be the invariant. L for the algebra multiplying C by B. Okay, so that means that's quite accurate here. Okay, so what is this? This is just notation. We unpack it for X.
Does it need to be C or can it be any field?
Sorry, we're working over a general field K. Thank you. It's lambda by B. Lambda K and X in L. Okay. This guy is contained inside KB. That's clear because it's actually just 0. So what I'm trying to say here is that this is a sub-representation. Okay. The vector space, the K, one-dimensional K vector space spanned by this invariant element V is a one-dimensional sub-representation. It's a trivial one-dimensional sub-representation, but still a sub-representation. If you remember when we spoke about representations, if we have sub-representation, then we can quotient it. Just in the same way you can quotient a vector space. You just check then the natural, the obvious action on the quotient is well defined, so you get a new representation. So therefore, we can consider V tilde. What is it? V tilde is V quotiented by this vector space. Okay, small v, big V. This is an element, that's a subspace quotient out of the representation. The quotient now if we look and note for any, so picking an arbitrary element inside an X, maybe here I should say and. Okay, this is just the action of this quotient. Now for any X, note that rho of X is equal to no, sorry. Let me go back. One moment, there's a step I did it. So now choose a basis what was the dimension? I guess we were going to choose it being n-dimensionally. So this is n minus 1. Notice this is of course an n minus 1 dimensional vector space because we're quotienting by one-dimensional vector space, therefore the dimension is n minus the dimension of the quotient, n minus 1. So we choose the basis of... Now, whenever we have a surjective map from one vector space onto another, we can always choose a splitting. Okay. So then, actually let me put tildes on these guys. Okay. Now, so now we can choose elements. Such that coset just to say, when you take the corresponding element inside of the quotient, you're going to get this element. It's clear. Just choose one. There's always going to, it's a surjective map, so there's always going to be something that goes on to each of these. Choose one of these elements. This gives us a new basis. Okay. And yeah. Then basis of B is given by V, which we'll denote by, this is the V we started with up here, and we're just going to denote it by V0, V1, Vn minus 1. Right, so we're starting at 0, so that gives us an n-dimensional basis for this vector space. Now, so now for F and L, we can, the end of the linear operators on V, the linear operators here, with respect to this choice of basis, will correspond to matrices. Okay? So it's going to be the form on the first column here, because the first basis element that we have is V0, which is V, and by assumption it's an invariant element of the representation, which is to say that the Lie algebra is going to act out by 0. So in the first column we've got 0. Okay. And then for the rest, well, but the point I'm trying to make is that if you look at this box here, in fact, this matrix here, just all I'm doing here is omitting the first row and the first column, and just taking this bottom right-hand corner box. So this guy is the matrix rotative. Okay. So there's a lot of linear algebra going on here. You should, but nothing that you wouldn't have encountered in your any basic linear algebra course. So think about this. Try to think about this carefully and become completely comfortable with it. But again, just remember it's only basically algebra, linear algebra that we're using. So now this means that the matrix rho, the rho of x is upper triangular if and only if this guy is upper triangular. Okay. That's clear because we don't care what happens up in this part here. Because whether it's 0 or whether it's not, the matrix will still, that doesn't do anything to the upper triangular, because the upper triangular is taking place. It's a condition of zeros down here. So we see that if there's zeros in this matrix, in the red box, then the larger, then row vector of the upper triangle, and vice versa, obviously when the other direction. So it's an equivalent condition, that row vectors upper triangle or row tilde vectors upper triangle. Now, but if we assume by induction assume that 1 implies 2 for n minus 1. Okay. Then that implies that there exists a basis such that row x is upper triangle. Okay. V tilde. Now, the argument that we made here is just for any matrix. So again, we just take this one here for which row tilde of x is diagonalizable, lift it up like this here, and that implies, therefore, row x is upper triangular, and we put ut for upper triangular with respect to v0, v1, vk. Okay. And then we're, of course you have to check if there's 0, but I think you can probably check when you start off just with the 1 by 1 matrix. Obviously, any 1 by 1 matrix is upper triangular. Therefore, you go off from there. That's the starting point of your inductive hypothesis. The starting point for the inductive process is it satisfies trivially, therefore it's done. Because we're able to go from n minus 1 up to n plus 1. So that's the first part. Okay. Okay, so let's do 2 implies 3. Which will of course give us that 1 also implies 3. So we want to produce, for this we want to produce a sequence of vector spaces, okay? Just remember, V0 contained in V1, contained in V2. These are strict inclusions. Okay. Vn. So it's a strict inclusion of this many, so it'll be just going up one dimension every time. Okay, such that L of Vk is contained, I'll use K, L is contained in V. Alright, this is what we're trying to prove. So, how would we define these Vk's? Well, we use the basis we had before, so choose. So let V0, V1, and V and minus 1 be as before. Okay, so we're choosing the same basis with respect to which everything is, all of the elements of the algebra are upper triangular matrices. Row of x for every element of the algebra is an upper triangular matrix. Okay. Now, what does that do? Now we use this to define the k's that we want. So, well actually it's going to be L, because k will get mixed up with the field, so k is a bad choice. So what is this? It's equal to the linear span over the field k of the elements V0, V1, and Okay, this is an L-dimensional vector space as it should be. So it's clear that then, clearly, okay, well, D0 is 0, and this is also for L. Well, I mean, we can make this n, doesn't matter. And it's completely determined here by assumption. Yeah. So this does the job of like, these guys are contained inside of each other. It's this nested sequence of vector spaces living inside here, such that the bottom is 0 and the top is the whole thing. The bottom is 0 by assumption. We don't need to define this because it's over there. But what we need to show then is that the action of the Lie algebra, so this is of course equivalent to x by v is an element of v to the L minus 1 for all x element of L. Okay. Just this is a more compact way of writing this. Maybe I shouldn't really use the brackets. I think that's probably quite bad notation. So let's put it up. Or of course here, no, this is wrong. What I really mean is this. So this, remember this idea that we have a representation, or we have this, we can think about it, a representation as a mapping to the endomorphism ring, or we can think about it as this pairing between the two of them, an action. And we use these two interchangeably. But now, but since rho x is over triangular, it just follows from matrix multiplication. That's like right. So we know that by 0 here, it's upper triangle. Okay, so these are all 0. So when I take any element here, let's just take the basis element. And it should be clear from this. You take 0 to 1. Okay, just taking the standard basis element, these are dots. And this is 1, hopefully that's clear, you should see what I mean. Then when we multiply, okay, we're taking a guy like this, and then we're multiplying. Then because you see, once we get down here, it's all going to be zeros. So this thing will actually be contained in E1, E2. You're only going to get components in the top part, which means that it's an element of it should be L. And implies that rho x is an element of L. And we're like, okay. So that tells us that 2 implies 3. Okay, so the next part that part 1 actually holds from the assumptions of the theorem, that's a more difficult proof. So we'll postpone that to the second part of the lecture and finish the first part here. Okay?